Hi everyone. In today's episode, I speak to Ayush Pandhi, a PhD student at the University of Toronto. His latest paper combines two things that have nothing to do with each other to reveal another completely unrelated property. More of that in a moment. So, thanks for joining me today, Ayush. How are you?
Good. Thanks for having me. I'm doing great.
Your supervisor is Professor Brian Gainsler, and he was actually on the show back in episode 105 talking about magnetism, which we'll get onto in a little while. So, for those of you who are interested in that episode, click on the links below and I'll have a link through to that. But today we're talking to Ayush, and could you firstly just tell me a little bit about your background and how you got into what you're studying?
Yeah, so as you already mentioned, my name is Ayush. I got interested in astronomy probably around middle school, and I guess for international viewers, that's the sixth grade. I used to watch a lot of National Geographic, and there used to be just tons and tons of science documentaries on there. And so that's how I really got started. I think it was a Brian Greene series, Fabric of the Cosmos. I don't know if you've
I,
seen it.
yeah, I remember that
Yeah,
one.
yeah. So I think that's the first one that really got me hooked. And I used to be a very annoying kid with all of my questions and just unrelenting questions. And so I always joke that astronomy is the one thing I never ran out of questions for. So I've just kept going until now. So that's really how I got started in astronomy. And then throughout high school and things like that, I started getting more into actually observing. So like having a telescope and going stargazing and things like that. Throughout university, I just kept going. And then, as you mentioned, I met Brian as an undergraduate, and then I started working with him now for my PhD.
Did you study science or did you go straight into physics and astronomy?
Actually, funny enough, in high school, I was in a business program, but I tried to take as many science courses as I could in the business program. And then for my bachelor's degree, I switched over to physics and astronomy. So I mostly did physics and astronomy with a little bit of math. I had a math minor, and then now I'm in a fully astronomy PhD program. So I've sort of fully transitioned into studying just astronomy.
So do you find that the business helped you in any way, or is that sort of a little bit behind you now?
Yeah, no, I mean, I forgot most of the actual business parts of it, but what it really helped me do is get better at things like public speaking and giving presentations and how to like organize slides and things like that really well. So I think it helped me in that aspect of giving like science talks and things like that. But
Mhm.
yeah, most of the actual like I don't remember how to do accounting really. So I don't know if I could fill out like your forms for your business anymore.
I don't think most of us can. So with astronomy, as you mentioned, you had a telescope when you were younger, and most people will think of it in terms of the visuals. So as you moved out of undergrad to doing your postgrad, how did you decide on what you were going to research in? How did you get your interest sparked in where we're going to go to in a moment?
Yeah, so really switching over to a PhD, you have to specialize in one particular topic or problem. And I think the first thing in astronomy, when you start to specialize, you sort of have to pick your favorite part of the electromagnetic wavelength. It's hard to just say, like, I want to do all of astronomy. You sort of have to narrow yourself into, well, I want to do optical astronomy. So things you can see with your eyes, all of the like fun pictures you see, or I want to do X-ray astronomy. So things that emit X-rays or gamma rays. So I ended up doing radio astronomy. So things that emit radio waves. And with that came a lot of magnetism, which I'm sure we'll get into, but that's how I started because my first project that I did, my first research project was about magnetic fields, and I really enjoyed that. And then after that is when I got introduced to Brian, and then I just continued working on magnetic fields.
So people tend to think about magnetic fields in terms of where we live on the Earth. So we all know about the North Pole, the South Pole, and the people who think they're a little bit smarter than everybody else go, aha, but the magnetic north is different to the geographical north and so on. How does that expand out and relate to the universe in general? So we're not just talking about iron in a core of a planet turning around and that's causing magnetic fields. Can you give us a bit of a background on magnetism in the universe and then how that leads into your area of research?
Yeah, so the way most people think about magnetic fields is like you mentioned about the Earth or like magnets on their fridge or things like that. But surprisingly, when we talk about astronomy, a lot of the things are like bigger, brighter, and crazier than what we experience on Earth. But magnetic fields is often the opposite. So the Earth's magnetic field, for example, is much stronger than magnetic fields we might just see in any random part of our galaxy. Because in Earth, as you mentioned, it's due to Earth's core. But out in the galaxy, we just have free electrons floating around, creating a current, which creates a magnetic field. And so those tend to be much, much, much smaller. But they're still very useful. So they help in things like how stars are formed, how all of that gas comes together, collapses and forms a star. It helps us figure out how very fast, what we call cosmic rays, but they're basically just small particles near the speed of light flying around our galaxy, how those move around, how gas on a larger scale throughout our entire galaxy shifts around. So magnetic fields are sort of part of every component of astronomy that you can study, but they're not something that you can really see. So a lot of people tend to either dismiss them or not really think about them as much because they're not abundantly clear. Like if you just look out into the universe, you're not going to physically see a magnetic field, but you will see its effects on things down the line, like a star, for example. And so that's where I really tend to focus on in my research, is figuring out ways for us to actually be able to see magnetic fields through different things that we can observe with our telescopes.
So with your latest paper, it was a bit of an accidental discovery looking at two other different things. Can you sort of run through that for us?
Yeah, so in my paper, I look at two different things. So what we call radio galaxies. So these are black holes in the centers of other galaxies. And when too much material falls in them, so like too much gas and things like that, they tend to emit a lot of polarized light that we can see. And then the other things are these sort of unknown objects that we don't really know where they come from, other than the fact that they're not within our own galaxy, called fast radio bursts. And using the combination of these two, because they both emit polarized light, what we can do is essentially figure out, okay, because both of these things emit polarized light from where they originate. So let's say it's polarized this way, let's say straight line, as they pass through other magnetic fields. So our galaxy has a lot of free electrons floating around. And those electrons have small magnetic fields of their own because they're essentially acting like a current when they move around. And so each of those electrons will slowly shift this angle a little bit and a little bit more until it gets to us. And so what we observe on Earth is a shifted angle from the original one. And based on, there's a lot of like little math that goes into this, but based on what wavelength of light we observed, we can figure out how much that angle has shifted from when it started, where it originated, and then when it ended up to us. And so each of these polarized sources sort of has an intrinsic way of telling us how much magnetic field or how much electrons and material was in between us and the thing that was emitting it. And so the challenge of this paper is trying to figure out, okay, can we figure out how much of that shift in the angle was due to our own galaxy versus other things from beyond our own galaxy, and then use that to try to figure out, like, okay, what would a map of our galaxy's magnetic field look like then?
It's kind of a bit like a magnetic Doppler effect in a sense, isn't it?
Yeah.
The question that comes to mind when you mention that and the shift of the angle of the magnetism is, how do we know what the original angle of that magnetism was going to be? So how do we know it wasn't already at that angle?
So usually this is done through a lot of math and coding. How we understand that angle to change is not the same at every wavelength. So usually when our radio telescopes, usually these big antennas, are staring up into space looking at these sources, they're usually observing between two frequencies. So we can say, for example, the telescope that I'm currently using, CHIME, observes between 400 and 800 megahertz. So that polarized angle will change differently at 400 megahertz than what it will at 800 megahertz. And so the way it changes is like a linear function that you can fit. So essentially what you're saying is, I know what I observe at 400, I know what I observe at 800, And then I know that it should be linear. So you can just sort of draw a line between them and then figure out, okay, what is the slope of that line? And that gives you this quantity we use to measure magnetic fields called the rotation measure. And essentially, it's as easy as that. In theory, it's fitting a line. There's a lot more complicated ways of doing it, but essentially, that's what you're doing. You're saying, I'm observing at these two wavelengths. It changes this much at one, this much at the other. You draw a line, and then you figure out its slope.
When you describe it that way, it sounds very simple, but I'm sure there's a lot of programming and mathematics behind it. But that does make a lot of sense. We tend to think of electromagnetic spectrum, and it is called the electromagnetic spectrum, but we tend to think of it as things ranging from infrared through to ultraviolet and the visible spectrum and so on, and what we observe. Where does magnetism fit on that, or is it a different scale?
That's difficult to answer in the astronomy sense. So magnetism, I mean, it does fit because it's the electromagnetic spectrum, but I don't think there's like a one-to-one equivalency. So magnetic fields, we sort of measure on their own. So of course, if you have like a stronger current, you'll have a stronger magnetic field. But we don't tend to sort of alternate between those two because we usually study magnetism and what it does to other objects on its own. And then we separate it out because not every astronomical object will emit polarized light. So everything will have like a strong magnetic field, even if it has high energy. So you really have to pick out the sources that will give you polarized light and also have high enough energy for us to see on Earth.
Can magnetism affect any of the polarized light along that electromagnetic spectrum?
Yes, but we don't see it at all wavelengths. So what I mentioned about how you can see it at 400 megahertz and at 800 megahertz. So that becomes harder and harder to see as you go to more and more energetic light. So if you go to infrared, it becomes harder to see, optical, and so on and so on. So you can only really see it at radio waves. There are some other ways to look at it in terms of like X-rays and things like that, but those are separate methods than the one we work with.
So is that a limit of our technology and observational capability, or from the actual science?
Mostly from the actual science, because I don't know how we could ever build something so sensitive that would be able to observe what we see at radio waves at infrared or something. That's sort of just, it's too far beyond anything we could make. So I'd say it's a science limitation.
With your latest paper, discovering that there's the magnetic angular shifts from distant objects and so on, what does that tell us about those objects?
So that tells us, first of all, just if anything has polarized light, that automatically tells us something about what's emitting it, because not all types of emission mechanisms will create polarized light. So that tells us it's similar to, for example, what a neutron star can do. And a neutron star will be a very compact object that's dense enough to create these directional beams. So all of its light is pointed in one direction and it's very high energy, but it won't be something like, for example, I don't know, like a planet, which won't really create strong polarized light. It'll just emit off in like infrared and optical and things like that. So it automatically tells us something about what's creating those objects. And it also tells us about what's nearby those objects. So for example, if there's a really strong magnetic field right next to one of these objects, then we would see a really big shift in that angle. And we could figure out, well, this is too big to be coming from our own galaxy. So there must be a very strong magnetic field near this object. Or if we don't see a big angle, then we'll know, okay, well, the magnetic fields around that object aren't very strong. And so we can sort of tease out little details about how these objects are emitting and also what sort of area they're located within.
It's basically helping us map a bit of the space between us and the object that's emitting it, isn't it?
Yeah, exactly.
So what's next for you, Ayush, in your research?
Yeah, so I just finished my second year of my PhD, so I have 3 more years to go. I plan to do more similar things like this, but focusing more on fast radio bursts. So fast radio bursts are exactly what it sounds like. They're bursts at radio wavelengths, and they only last a few milliseconds at most. And so we don't really know what they are. They were just discovered just over a decade ago, I think 15 years ago now. And so a lot of people are working on trying to figure out exactly where they come from. And the collaboration that I'm part of, Chime in Canada, is one of the leading collaboration in terms of fighting these bursts. So what I'm going to do next is look at these bursts, again, using their polarized light, and try to tease out exactly what I just mentioned about where these bursts could be coming from. Are they located in other galaxies? Are they located near black holes? And what sorts of emission can be causing them? So that's sort of next on my radar.
How much do we know about them, apart from the fact that we can receive the signal? Do we know how far away they are, what directions they're coming from, anything like that? Or is it just totally random at the moment?
So we definitely know that they're coming from other galaxies. And the reason we know that initially was because one of these effects, like I mentioned about how the polarized light changes the angle, there's also another effect that disperses the amount of light that we can see. And so that sort of it's a proxy for how far away things are, because the more free electrons are between us and another object, the more dispersed the light will be as it comes to us. And so that told us that there was too much dispersion for these sources to be coming from within our own galaxy. And so that was our initial hint that they were coming from beyond our own galaxy. And then now people have followed up on some of these sources and pinned them down specifically to other galaxies. So we do know that they're coming from other galaxies. Some of them only go off once, while others repeat. And I think there's a couple that have been shown to repeat somewhat periodically. So on the order of days to years is what we think that those bursts repeat on. There's some other things we know about generally where they are, but there's no clear picture. So for example, one was located right in the disk of a galaxy where there's a lot of gas, and there's a lot of new stars forming, and a lot of things are happening. And another one was located in an old cluster of stars where there's no new stars being born, nothing's really happening, there's not a lot of gas. So there's a lot of conflicting things about what we know, but that's because we've only been able to study sort of individual events rather than having so much data that we can study them as an entire population and say, these are the statistics, and this is where most things come from, and this is what most of their environments look like. And we're sort of transitioning into that stage now.
Well, that sounds very exciting. So once you get a bit more information about all that, we would love to have you back on the show.
Yeah, of course. I'd love to come back on.
Well, thank you very much for your time today, Ayush, and we look forward to hearing more from you in the future.
Yeah, thank you so much for having me. This was fantastic.
Thanks for listening to the show. You can check out the Brains Matter website at www.brainsmatter.com, and you can find all the other episodes of the show there. There's also other information on the site, such as guests who've been on the show and subscription details. You can also find Brains Matter on YouTube, so make sure you like and subscribe if you're a YouTube listener. If you want to support the show, please consider becoming a Patreon at patreon.com/brainsmatter and signing up to one of the options there. Or you can donate either once off or regularly via PayPal. All you need to do is click on one of the PayPal donation options on the right-hand side of the website. If you have any comments or suggestions, you can leave an entry on this episode's show notes on the webpage or on YouTube, or you can send me an email. All my contact information can be found on the Brains Matter website. The theme music Soul of the Machine was composed and performed by Clive Weeks and is used with his permission. I hope you enjoyed the show. Bye for now.